Welcome everyone. In this example, I want to look at how to relate the entropy of the universe to spontaneity calculate or spontaneity conclusions. And our specific example says to calculate the standard entropy change of the universe for the reaction given here. So some graphite reacts with hydrogen gas to form methane, and we're given the entropy change of the reaction and also the enthalpy change of the reaction. And we're asked, is the reaction spontaneous under standard conditions at 298.15 Kelvin? All right, so our first question is, how do we calculate the standard entropy change of the universe? And if we recall that the standard entropy change of the universe, so the second law, is given by the sum of the standard entropy change of the system plus the change in the standard entropy change of the surroundings. All right, so the first one, or the entropy change of the system, is quite easy because the system that we are considering here is of course the reaction itself. And if we consider the system as the reaction, that means our system's entropy change is just our reaction entropy change. So, and that is given as minus 80.8 joule per Kelvin per mole reaction. All right, so that's the first one. The one that takes a bit more thinking is, of course, the entropy change of the surroundings. Because to think about what happens to the surroundings is affected by the reaction in terms of how much heat is released or absorbed by the reaction. So if heat is released to the surroundings, then the surroundings must absorb that heat, right? And we assume that heat is reversibly absorbed by the surroundings because the surroundings is so large that the reaction beaker won't be able to give off enough heat to disturb the surroundings in any significant way. So that heat must be given off in a reversible manner. If the reaction, if the surroundings must provide heat to the system, in other words, the system absorbs heat, then the surroundings must provide that heat. Right, so then what we must think about, what parameter would be able to give us the information regarding what a system, what kind of heat the system absorbs and or expends. And of course that is the enthalpy. Right, so that is why we can use the enthalpy of reaction. So our first situation here is to calculate the entropy change of anything. We need the amount of reversible heat transferred to that or the amount of reversible heat transferred at a given temperature. And in terms of our surroundings, it will always be the negative of whatever the system did, right? So like we discussed, if the system expels heat or gives off heat, the surroundings must absorb the heat. If the system absorbs heat, the surroundings must give that heat. So the relationship between the system's heat and the surroundings heat must be the inverse of each other, right? So that reversible amount of heat that the surroundings must, or the heat exchange that the surroundings has, is connected to the system by being the negative. And we know that the heat that the system requires or gives off at constant pressure is equal to the enthalpy, right? Because that is the heat of the system. The heat of reaction is called the enthalpy. So in this case, it is equal to negative the enthalpy of reaction divided by T. All right, so we're given the enthalpy. It's an exothermic reaction, so it means our system gives off energy to the surroundings. In other words, the surroundings is absorbing this amount of heat. So in other words, it should be a positive quantity, and that makes sense. If you take negative the enthalpy, you will get a positive quantity for the surroundings. So we see the surroundings absorbs 74.8 kilojoule per mole. Reaction divided by the temperature, which is 298.15 Kelvin, right? So let's just go through this again. Of course, the way to calculate S, just in general, right? So the change in entropy for anything is equal to the amount of reversible heat transferred to whatever you are looking at, divided by the temperature at which that amount of heat was transferred. And specifically looking at the surroundings, so we can apply this definition to the surroundings. Of course, the relationship between the system and the surroundings is the inverse of each other. Then we recall that a system, the heat, regarding heat and the system will always be the enthalpy, right? Because the heat given off by the system will be the enthalpy. If a system is exothermic, that means it has a negative enthalpy. If a system is endothermic, it has a positive enthalpy, right? So the heat at constant pressure is called the enthalpy. All right. So, and that's how we got to this point. So if I calculate this, you should get 0.250, etc. kilojoule per Kelvin per mole reaction. And if you notice, our system is entropy change at the moment is in joule per Kelvin per mole, and our surroundings at the moment is in kilojoule per Kelvin per mole. And we of course have to sum these two things, so that means we can put them in the same units, so we can multiply this by 1000 to get it into joule. So this becomes 250 joule per Kelvin per mole reaction. Alright, so let's go ahead and calculate the entropy change of the universe. So that's of course minus 80.8 plus 250.88, and if you round this, you should get, so I think it's three significant figures. So 170 joule per Kelvin per mole reaction. All right, and this is a positive quantity, right? So it's larger than 0. Right. So the last question is, so that's the standard entropy change of the reaction, of the entropy change of the universe for the reaction. So then we ask, is this reaction spontaneous under standard conditions? And to do that, we must say yes. Therefore, because the standard entropy change of the universe is larger than 0, this implies that the reaction is spontaneous. At 298.15 Kelvin. Alright, because we had an increase in the entropy of the universe. Alright, interestingly enough, notice that we had a decrease in the entropy change of the reaction, but there was an entropy change in a positive entropy change in the surroundings, and that actually dictated that the entropy change of the universe was positive overall, and that made that the reaction was spontaneous. Alright, so even though this system goes from 2 mole gas to 1 mole gas, which is why the entropy change of the reaction is negative, as expected, the system has a decrease in its entropy, so its entropy change is negative. The overall change for the universe is positive because of this negative enthalpy. And that makes the overall process spontaneous. And that's a very astute observation to make, because that is why things actually happen. Even though in terms of the system it might not be favorable, we're going from 2 mole of gas to only 1 mole of gas, that is not that favorable. But because the surroundings will be affected in a positive manner, the system is driven towards the right, and it will eventually it will be driven towards equilibrium. So it's a spontaneous process towards equilibrium. All right, so that is it for this. Remember, so if you need to determine the entropy change of the universe, you do it by doing the sum of the system and the surroundings. The surroundings you calculate through the amount of reversible heat, and you can relate it to the system through its enthalpy. The system is always our reaction, so you want the enthalpy change of the entropy change of the reaction. And of course, if you need to determine reaction spontaneity, you must look at whether or not the entropy change of the universe is larger than 0. All right, so that's it for this example. I'll see you in the next one. Thank you for watching, and yeah, I'll see you again.